And I think we're live.
We're live.
We're live.
Earthsite.
Welcome to the Earthsite podcast, or Earthsite.
Who knows?
Who knows? We'll figure it out.
Yeah. So, AI for Earth. Are we at the peak hype cycle?
Oh my god. Geo AI. This is a Geo AI podcast.
Embeddings only.
Embeddings only.
But actually, we do want to talk about embeddings, right?
Definitely. I mean, I think everyone wants to talk about them right now.
Everyone wants to talk about it. Everyone's hyped about it.
Yep. Yeah. And I think this is the few times in my life where I feel like I actually have the privilege of like maybe having been ahead of the curve somehow.
Maybe.
Compared to
I think
the
on a piece of the curve, you know?
Yeah. But
we were kind of early, I guess, in the grand scheme of things.
Yeah. So we worked on embeddings at Earthrise.
Earthrise, yeah. Now Earth Genome. Yep.
And we had worked on a retrieval tool called Earth Index that leveraged embeddings in 2022.
2022. I think that's right.
Yeah. So that's the background behind all of this. And
But we kind of wanted to, well, at least I was hoping we could take a little bit of a step back before we talk about what we did and maybe our opinions about what's happening now. But like, maybe it's helpful to talk about, how stuff started, like how people used to do work and how a lot of people still do work and why people even care about embeddings to begin with, you know?
Yep. Yeah. Well, I think I'm actually probably less qualified to talk about this than you, because I would say I mostly started doing work after I started working on embeddings. So I think maybe you should kick this one off, Krishna.
Yeah, I mean, and honestly, I'm not super qualified about the history. I think the important history to mention, which hopefully everybody already kind of knows who's listening to this, is that Landsat in the 70s was kind of the beginning of everything, right? From like public Earth observation, imaging in the visible and the near infrared, and then the continuity of that mission to now, as well as all the other missions that have launched, like Landsat and MODIS, and Sentinel since then, and the applications that people are working on, like vegetation, Landcover mapping. Like that's been happening for a long time. Like I think that's just kind of important. Yep. I don't think people really appreciate how many algorithms are really developed kind of like a long time ago. And like you're pretty qualified to talk about like a land trender and CCDC and stuff like that. With these great like Earth Engine implementations where you can do change detection over decades, kind of arbitrary change detection, right? And like, so it's not that we've been just like in the dark ages in the cave, like scratching at a single geotiff. Like people have been doing real work for a long time with a lot of well understood techniques.
Yeah. And again, I guess the context is that there's a lot of hype, maybe a lot of promise with embeddings, but a lot of the things that people are impressed with when it comes to embeddings, I guess the point is that there's like been existing algorithms to do these things for a very long time already. Like you mentioned, Landtrender and CCDC for change detection or breakpoint detection. And so, yeah, I guess it's a good place to start by talking about what we think is the baseline, right? Like what we think already exists and is already sort of operational and usable.
Right.
Yeah. So Landsat 1, near infrared, NDVI, which is arguably all you need, big public missions. I mean, it really feels like there was like already had been this huge trove of data that was maybe locked away behind, not being able to access it at scale,
Right.
the software tools being a little janky or just not that accessible or just not that widespread, to be honest.
Yeah.
Yeah. And so,
And
yeah.
NDVI is maybe like a good framing to talk about how problems have maybe classically been solved and maybe are still solved sometimes. Like I use these kind of techniques all the time. Like
Yeah.
you're like formulating the thing you're actually trying to look at. You
Yeah.
are looking at the data. You're thinking about remote sensing techniques that are relevant to like map your particular problem. And so like NDVI, I think, is a great example of that because it's super useful for vegetation, crops, but it's actually also really useful for built areas, like really low NDVI in built areas with impervious surfaces. And then like you might play around with thresholds, you might do some adaptive stuff, you might think about what type of composites you want to calculate, and then you'll kind of like build your solution iteratively, I guess, is one way to say it. Like you're starting from the data, you're trying to like maximize the amount of signal through these like, these bands that are already very, very targeted at particular parts of the electromagnetic spectrum because like
Yep.
they are important for mapping the types of problems that you can solve
Yep.
from Earth observation. And then you're kind of like building your solution out. And I think embeddings, the thing that it does that's very seductive is that it kind of flips all of it on its head, and it's like you don't have to do any of that work, right?
Yeah.
You just need to click. You just need to have an example of the thing that you want to find, and it's just going to do it for you.
Yeah.
And so I think that's very seductive. But and I think we're going to talk about why we think it's problematic in a lot of ways. But I think that framing, like that difference, is very interesting.
Yeah, absolutely. I mean, I think the point you touched on about thinking about what the sensor you're using is designed for. Why did we choose these bands? What physical processes are they sensitive to? With multispectral, at least, it's pretty obvious that it's mostly vegetation, and different kinds of vegetation, sure, but these are things that signals that are already present in the data
100%.
and are associated with just a myriad of things that we might be interested in, human activity, things like that, just measuring the imprint of human activity on the surface of the planet. Vegetation and declines and increases are just great proxy signals for that to begin with. And so, yeah, it's to be honest, I guess sometimes I feel a little confused as to why we're so excited, because there's just so many products already that don't leverage embeddings that are just insane. Like just
I think
yeah.
what the embeddings people would say is that, well, yes, like there has been tons of amazing work done with traditional techniques, but the amount of time it takes to build something like that, the number of data scientists you need or the software engineers you need to like build that kind of thing and actually deploy it and get real results is prohibitive. So it's like super expensive. And then if you solve one particular style of vegetation problem and then you're trying to solve a urban problem, like the techniques basically don't scale and you're starting from step 0 every single time or pretty close to it. And so basically this model doesn't work, right? That like you need a different way of doing things. I think that's what they would say.
I've been thinking about this a lot, and I think sometimes, I think anytime I've tried to solve a problem, that the bit that embeddings is supposed to solve just hasn't really turned out to be the bottleneck, maybe.
I mean, I 100% agree. Yeah.
Yeah. And I think it's sort of maybe a bit of a fallacy to say like better, faster, cheaper. Like, labeling is an intensive process, but at least in Earth observation, I'm not totally convinced of that. Or I'm not convinced that it's the hardest bit. To be honest, accessing the imagery at scale is, for me, often the hardest thing, right? Like
Sure. It's
Earth
still the
engine,
data access.
if Earth Engine doesn't have the geotiffs you want, or if you have to purchase them, or if you need high res, or and all the problems that come with that, like that still feels like the bottleneck to me.
Yeah, I think the other thing that feels interesting to talk about here is like the validation bit. And so this is something that I have dealt with a lot recently in terms of like validating stuff. And I would say most of my job is validation, like checking the outputs of models to make sure they're right. And when they're not right, like fixing it. And, you know, when we were talking about like that traditional workflow of like, you know, formulating the problem, examining the signal, trying out techniques, adjusting thresholds, tuning knobs. What I realized is when you're doing that process, you're actually validating like almost every step of the way.
Yep.
So in a sense, like you're spreading the burden of validation kind of like across the life cycle of the development of your project. So because you're looking so much at the data and the signals, you're actually like you're doing a lot of validation work along the way, and that turns out to be super helpful later on when you have to actually figure out whether your outputs are right. And I think what embedding's the thing is that you can make an argument that some of these embedding tools are sort of like human in the loop validation, in the sort of like most generous interpretation of it, but because you spend so much less time up front and validation is not really baked into the process, you end up with this result at the end, and it's like, are you going to check? Like it becomes this huge thing to try to check, and it's like you haven't done any of the work to look at the relevant signals along the way, so it's like you're actually kind of lost.
Yep. And I think there's also something, you kind of have to acknowledge that with a lot of these problems, unless you can pay someone to do a crop tour, or you have boots on the ground, or you can pay someone to really actually get ground truth in the literal meaning of the sense. Like it's just you have to be able to justify the quality of the map to yourself. And there's just a point where you say, these are the reasons why I think this is a good map. And I think there's this process of going to look at the data yourself, learning the patterns yourself, overlaying external data sources, things like that give you that sense of, I guess, confidence to say, this is why I believe this map is correct to this degree, or something like that.
It's like the explainability thing that I feel like everybody used to talk about before LLMs were a huge thing of like, oh, machine learning's not super explainable. Your CNN's making some classification. It's like you can plot some activation layers and get some edges out, but it's like you don't really know why it decided something was a car or something like that, right? Like, people used to talk about that. People don't talk about that much anymore.
No.
But with remote sensing, it's like, it's kind of like an even bigger deal, right? Because if you're justifying your like crop yield model to a customer and your justification is like, well, NDVI is like this real signal, and then we used EVI, and then we used Savvy, and then we incorporated these other things, and this is where we know they fail, and this is where we know they succeed, and so like these are the error bars that we can put on it. You can make some reasonable claims and not sound like a total dumbass. But if it's like, my embedding told me that this was this.
Trust me. Trust me, bro. Like I think, no, absolutely. And this is like I guess it's like a technological problem, right? Like you can only go so far definitely with, medium resolution, 10 meter pixel, Sentinel-2 or Landsat. I'm actually starting to become, having not touched that much high resolution imagery myself, become pretty high resolution imagery pilled, so to speak, in that like most projects, if you're serious about really knowing what's going on, eventually, you need to allocate part of your budget to high-res imagery, to tasking, to validation, basically, right? Verification.
Definitely.
And it's, maybe there's also this allure that like, oh, this is like all open data, and we could build empires on top of it, right? Like we just need Sentinel, we just need Landsat, and for some problems, you can argue that this is,
Yeah.
it's good enough, right? Like crop mapping, maybe like your fields are a certain size, and you've got enough historical data or something like that, and sure, but there's just so many cases where you get to the end of a project and you're trying to justify it both to yourself, to a customer, stakeholder, or whatever, and you're just thinking, man, there's just so many holes in this. Like there's so many more acquisitions we need. There's too many clouds or something like that. So yeah, totally agree.
Yeah, definitely. I mean, I've been touching a lot of high res recently, and I've never looked at more high res than in the past couple of years, and it's definitely a whole different ball game in terms of just how you go about doing the analysis, and then both like what you can see in the high res, but then how truly limited you are in scale. So,
Right.
because it's like you're never getting high res on the same week over a large area. Like it's just not happening.
Right.
Like the way tasking works and the way
Yeah.
and this might not be as true for people who truly have unfettered access to like all of Maxar, for example, but
Right.
but if you look at planets like SkySat tasking, for example, so that's like something I have access to and I get to look at, and their catalog, and it's like, the footprints of their collections on a day-to-day basis. I mean, these are tiny footprints. They're looking at
Right.
like this port over here and this breaking news event over here of this fire, and
Right.
it's not broad-based coverage. And so
Yep.
this whole like tip and queue thing of like tip with the low res, task with the high res. I mean, I think there's definitely real value in that, and I think that but what I don't know is if everybody is approaching the like Sentinel-2 game with that lens of like, this is
Yep.
gonna almost by definition be incomplete, but it's a starting point,
Yeah. I mean, I think they're almost certainly not. At least based on my experience, I think, and again, maybe this is okay. I mean, part of the problem is that with Earth observation, you can make such cool demos. Like you can really make
and embeddings
mind-blowing
make the
demos.
best demos.
Embeddings make incredible demos. I mean, but even just to a layperson who hasn't really looked at imagery before, showing them a Sentinel-2 time series, showing them a factory being built, or something like that, I would say that's pretty mind-blowing. I mean, my first experience with that was mind-blowing. And I think it just sets people's imaginations going a little bit about like the art of the possible.
Right.
But when you actually try and solve the problem to the end using Sentinel-2, you get to a point where you realize like, deforestation happens in tropical areas, and it'd be really great if we wanted near real time, we'd probably have to use a different sensor, or we'd probably have to send someone out in the field to verify or something like that. And it's happening at scales where this just isn't feasible. And so I think it's seductive. The demos, they're just so great. They're great.
They are great. And I feel like we built a lot of demos and we got super excited about them. We were like, oh my God, we solved it.
Yeah, I'm still excited about it, but I think it's like the seduction of technology, right? Like it's shiny, it's new. I mean, once upon a time doing Sentinel-2 at scale, global scale, was new. I mean, it's still difficult to do. It's still but I think people get excited more about technology than they do about problems and solutions, which are like sort of old news. Like, yeah, we know the Amazon's getting deforested. Yeah, we know biodiversity is under threat. Yeah, we know all of these problems, but what can we do about them? And I think technology is kind of seductive in that sense, where it's like, oh, could we solve all of these problems? Should we maybe talk about what embeddings are before we start talking about
Absolutely. Let's talk about what embeddings are. Yeah. Do you want to take it?
Oh, this is...
Let's get this big brain on it.
This is... Get some big thoughts out of it. I think of embeddings just as sort of like compressions, just
Compression.
sort of,
Yep.
yeah, like compressed representations. Just sort of at the simplest level, I think of them as summary statistics. I think
Yeah.
of summary statistics as a form of embeddings, and I guess we'll
Yeah.
talk about why I think that, mostly because of you. And so I just sort of extrapolate from there, right? Like if a summary statistic can be an embedding, like average greenness of a pixel over a year, or average greenness of a tile over a year.
Mean and standard deviation, NDVI, two
Right.
bands. Like
Right.
that's an embedding.
Yeah, that's a compression, and so why not? And
It's a huge compression, and it's
Yeah.
hugely useful.
it's hugely useful. It captures a lot of the variation you might be interested in. And so if we just start from that idea, then you could just imagine more complicated summary statistics.
Right.
Some, chained together maybe, or some generated not by some sort of traditional statistical method, but maybe a neural network, right? Like
Yeah.
passing
Yep.
something through a neural network and getting the latent representations out. So that's kind of how I think of them.
Yeah, I
Yeah.
think that's great. And like I'm curious, like do the word embedding and search live in the same part of your brain, or do they live in separate parts of your brain?
That is a good question. I actually think they live in separate parts of my
Yeah.
brain because you could just calculate the summary statistics and just train a classifier over
Train a model right on that.
do something
You don't have to think about
unsupervised,
search. Yeah.
Yeah, and actually I think maybe like search and human in the loop search is probably maybe the more interesting aspect of all of this.
Right,
but,
right.
But yeah, I think they are separate, I would say.
Yeah.
What about you?
No, I think they're also separate for me. I only brought it up because I was kind of like really keyed in on the search idea, like, right as I was coming into Earthrise to work on Earth Index.
Right.
And search was, at that time, the thing that I thought was the most interesting. And I feel like embeddings were the way into search.
Right.
And so I was thinking a lot about search. But I think these days, like kind of what you said, they live in very separate places in my mind, probably because I have like trained models on embeddings directly,
Yeah.
like what you said, like without a search context. But I do think search is interesting. I wonder if this is a good segue to talking about what kind of work we did on Earth Index in the beginning and how we thought about it.
Yeah.
And so I love the like summary statistics setup. And so, so, I was really focused on search. So this is basically, this idea that like you click on something or you click on a few things
On a
and then
map. Yeah.
on a map, right?
Yeah.
Like you click on a gold mine and you can find many more examples of that thing basically with search in a similar way that you go to Google and you search for something and it searches through the web, which is indexed, and you get the most relevant results back, right? And it's this ranked order list.
Yeah.
So the idea that you get this ranked order list back of the thing that you clicked on,
Yeah.
and the more examples of that you had, that search kind of just kept going and going and going and going. And so, yeah, I guess this was in 2022. So, I had the search lens and I also had the tiles lens. And so, with embedding fields, like the stuff Google just put out recently, that's all at the pixel level. At the time, I was like very set on tiles. So again, thinking about like the highest res data that we have available at scale freely, which is Sentinel-2, 10 meter resolution. Most things or objects, like, separating it from like Landcover, right? So Landcover is a pixel-wise problem, at least I think about it that way, but objects, like, again, gold mines, these are things that are 10 meter resolution. They're larger than a pixel, right? Like they kind of fit in a small tile. And so, and tiles are another form of compression, right? So it's like, it's not compression in the temporal or the spectral domain, it's compression in the spatial domain. And so it just means you have less data to look through, which is also super convenient. And so, had the tiles focus, had the search focus, and then the actual embedding. Like, I came in being like, how do you create the dumbest, simplest baseline, like basically the mean standard deviation or like the random forest equivalent for a classifier of like an embedding, something that will like work and will kind of suck, you know?
Yep.
And so, so, my idea was just to like, I guess I just drew upon experience from working on a bunch of different problems to be like composites.
Right.
Composites are super useful for all kinds of problems because what they're doing is they're giving you like this reduced view at what happened at this place at some point in time during the year, right? Yep. And so I remember when I was doing like crop modeling, it's like, I take all these composites at the different time of year because it's a pain in the ass to try to deal with variable cloud cover across the year. So these like percents of NDVI across the year are super useful. And so I was just like, well, you could just take every band from Sentinel-2 and then maybe pick your favorite remote sensing indices, NDVI, NDWI, and then you can just calculate a bunch of useful composites: the mean, the min, the max, standard deviation, some of the second order stuff, the kurtosis, the skew. So basically the idea was like sample the distribution across a year of every one of these bands. We don't know which band is useful for search, right? Because we want it to be useful for all kinds of problems. Yeah. And so that works at the pixel level. And then to do it at the tile level, I did something even dumber, which is like take the same reducers and just do them spatially as well as temporally. And then you have an embedding, right? And, we called those expert embeddings. And I think it's safe to say that me and you and everyone was like shocked at how good they were.
Yep. I mean, that was, I think, a big turning point for me in terms of thinking about how to solve problems in Earth observation. So again, just to summarize for people what these expert embeddings are, and actually, I believe the Earth genome still calls them expert embeddings to this day. Maybe they should call them Kara embeddings.
No.
So basically, take a tile, maybe, I think we did 32 pixels across.
Yeah.
Square tile, 32
so 320 meters across.
Yeah. Each pixel, you take a year of data and you calculate the mean, standard deviation, a bunch of statistics for all the different bands. And then across at the tile level, you do like a mean or a median summation spatially over those statistics. And you have a one-dimensional vector that essentially represents 32 by 32 and then in the time dimension, a year, and then in the spectral dimension, 13 bands or maybe 12 bands.
And I think there's 12 bands and 2 indices, so it's 14, yeah.
Yeah, and then that's your embedding. Like no neural network involved.
No neural net, no machine learning.
Yep. Yeah, and I think you had a lot of doubters too. I think
I had a lot of doubters. I mean, which is great. I mean, I think the nice thing about this is we had built like enough of a like application layer that we could like throw these embeddings into a front end and basically try them out on a bunch of problems. So it was like really nice. Yes. Yep. We were in a really fun iterative stage for a while where like everybody was trying their embedding and just plugging it into the system and seeing how well it worked. That was like super awesome. But I think the insight there that's like, I don't even know if it's insight. It's like, I think the thing that it revealed to me, which I didn't expect before, is something more about the data itself, which is that like medium res data, that its superpower is actually like solving the problems where you need temporal information to solve it.
Yep.
It's really not for spatial problems, like it's useful for problems where the dynamics are different throughout the year and they're different in a way that you can capture and measure and like classify against other things like, aquaculture and gold mining. And we were looking at like, these like open sewage waste pools in Alabama, which like had this like huge NDVI signal sometimes when like algae were like eating this waste, and it's super gross stuff, but it's like very interesting temporal classification, and that's like these embeddings just really excelled at that. And even when I know you had like done a ton of work after this to then really push us forward with like like doing ImageNet based embeddings, which I think you should talk about, and some of the other models. Like those models ended up being really good at some spatial problems. Expert embeddings weren't, but then I felt like there was always this gap of those like neural net based approaches failing to capture a lot of the like temporal stuff that was baked into expert embeddings.
Yep, absolutely. I mean, I think when we saw how well the expert embeddings worked across a variety of problems, including detecting waste pools in Alabama, illegal gold mining in the Amazon. I think you did some work on the Rohingya crisis in Myanmar as well, using expert maybe.
Yeah.
And they worked really well for that. And again, all of these problems related to vegetation some way or another. Right, like
of course.
Vegetation or water, some way or another.
Vegetation change.
Yeah. And then I think someone asked us about confined animal feeding operations. Like, hey, can you guys detect these?
That's right.
These long,
CAFOs.
Rectangular, metallic buildings where
a bunch of animals are stuffed inside.
Yeah, poultry, where chickens are just, it's pretty terrible. Slaughtered and kept in terrible living conditions. And the first thing
they didn't work well for that.
Did not work well for that, and which made sense. Again, no spatial information captured. And I felt like looking at these things we were trying to detect, their shape was so distinct. And I remembered, reading in the original geovisual search paper by Ryan Kiesler and the folks at Descartes Labs that they had trained their own autoencoder, but they had just used pre-trained ImageNet weights on RGB images, and that they had worked really well too.
On NAPE, right?
On NAPE, yeah. And I just thought,
which was I think the best part of the demo. Like if you go to GVS, like the NAPE stuff was the most compelling. It
was the most compelling, like the wind farms and everything like that.
Yeah, the Landsat stuff was like kind of cool, but it didn't really work.
It was a cool demo. But and I just thought, okay, well, these guys say that ImageNet works pretty well. Like, let's just try RGB Sentinel ImageNet embeddings as well as the expert embeddings. So now we have a set of embeddings that are just for spatial problems, RGB, and a set of embeddings that are for spectral temporal. Were those just
mean composites or something?
I think they were mean composites too. Yeah. And there was a lot of debate at the time about, like, does it make sense to generate embeddings from a neural net on composites? Should we generate embeddings on every single scene and average those? And I always just feel like just try the easiest thing first, right?
Yeah,
the easiest thing was clearly just try the RGB composite, and again it made for a really great demo.
It worked.
These ImageNet embeddings, I don't think in our tenure there that we ever really beat them. Not that we had strict benchmarks, but like I was using the tool every day. I was running searches every day, trying to get a sense of the embeddings, get a feeling for them. And the ImageNet embeddings are just really good. And I remember on top of that, I had run this massive pre-training based on Landcover.
That's right.
I had run this huge, I spent probably like 40.
You spent a shitload of money.
Yes, I spent a lot of, hey, these were credits, not money, to be fair. And we needed to spend them. Hutch from the Earth Genome told me, hey, we've got these credits, we need to spend them. And so spend them I did. I ran some massive self-supervised learning experiments, which, this is what we called foundation models at the time. And
we didn't call them that at the time.
And well, we didn't know what foundation models were.
No, we didn't.
And
still don't.
And I think part of this was like definitely lack of experience from my side. Self-supervised learning is hard. I didn't formulate the problem well, but
so you were trying to just solve the in the self-supervised setting, like solving the Landcover problem?
Yeah, I believe that's what
Got
I
it.
tried to do.
Okay.
I sampled, I think Dynamic World had maybe just come out, and I thought,
Ah,
ooh,
right.
like I don't even need to train on composites. I can just
Yeah.
infinitely
And
sample.
I think it was a good thought. It's like, Landcover is basically an embedding,
Right.
right? It's
Yeah,
basically like a
absolutely.
reduction of what you can see from Sentinel-2 into these, 9 or 10 classes,
Yep.
these broad-based classes. I mean, that's an embedding, right? So
Yep.
it's like, that makes sense. It's like, oh, if my model knows something about Landcover, it probably is pretty general at solving whatever problems a user might want to solve, right? Whatever thing a person might click on.
Yep. Yeah,
So it's
absolutely.
good intuition. I remember being like, yeah, that makes a lot of sense. We should try
Yeah.
it.
And I was like, we have these credits, we need to spend them, like why not? I felt pretty confident that we were going to get something out of this,
But
just
you're a
because of
confident guy.
this is true. This is true. This is true. I mean, yeah. Both of us, Krishna, I would say. To be
Yeah,
honest. But,
sure.
but I just thought that the ImageNet embeddings worked so well, and I just thought this is so dumb. These models are trained on cats and dogs, and they can recognize
Cats and dogs.
features in remote sensing. That if I do some sort of self-supervised problem or even a supervised one, just trying to learn the weights of the dynamic world model, surely
Right.
there's information in there, and I just realized it wasn't working out. I had sampled my tiles well, like the neural networks do not need that much information to tell the difference between a desert tile and a water tile. Like if you just average the RGB bands, you could probably tell the difference. And then I also remember going to look at ImageNet a little more closely and realizing how difficult of a problem ImageNet is, because there's 1,000 classes. You have to tell the difference between lots of different things, but examples are the difference between a husky and a malamute.
That's
Like,
right. That's right.
That's
It's not
difficult
just
for
dog cat.
no. It's like this is a type of dog. This is a
Yeah,
type
yeah.
of Arctic, maybe slightly stubborn dog that likes to sing, and there's two of them, and you have to tell the difference between the two of them, and that's difficult for humans, let alone
And
a machine.
And I think we were talking a couple months ago or something, and I think you said something off the cuff that kind of like changed my mind on something, because I feel like the common knowledge, or the common like intellectual brain trust is like, well, you need to pre-train on satellite imagery for your stuff to work well on satellite imagery. That's the common knowledge, right? It's like, big EarthNet, or like, take any of your other
Yeah.
things that are, it's like natively trained on Sentinel-2.
Yep.
And then you can fine tune it from there.
Yep.
And then I think you made this offhand comment of like, but there's so much less spatial information in
Absolutely.
satellite imagery than there is in these photographs that we take,
Natural images,
and
yeah.
natural images. And so it's like, why should we pre-train on satellite imagery if our goal for the model is to key in on spatial, like subtle spatial differences?
Yep.
Right? For like, and really this is a high res thing, but if that's our goal, then it's like, is training on satellite imagery the best? I don't
Yep.
know. I feel like after we talked about that, I feel like I used to be in the other camp where it's like, well, duh. It's like,
Yeah.
multispectral, this is the data,
yeah.
but I'm not so sure anymore.
Well, it's funny you say that because after we spoke about that, this DINO V3 paper came out.
Right.
And I don't want to get this wrong, but I'm pretty sure I looked at the tables. They did some Earth observation experiments.
Yeah, yeah.
And they had a version that was pre-trained on their natural image dataset, just RGB.
Mm-hmm.
And first of all, that model beat a lot of Earth observation specific foundation models that were multispectral on a lot of benchmark tasks.
Yeah.
And I think the benchmarks are totally flawed anyway, but still, And they then pre-trained, or I think maybe they fine-tuned a DINO V3 version on Maxar RGB imagery, and it didn't do that much better on a lot of high-res benchmarks. if I recall correctly. I need to go check that. But I remember
Interesting.
looking at that and thinking, oh, I guess things just look like things, you know? And
Right.
whether they're things in satellite imagery or things that are, you know, dogs or cats, things are things, and the features we use to determine what things are what things are sort of universal, maybe.
Maybe.
Maybe. And and so that's another point for the don't just pre-train on satellite imagery. And I guess, you know, there's just more diversity in natural images than there are in
Right.
satellite imagery, right? Like if you just close your eyes and try to imagine the tones of your typical satellite image, your Sentinel-2 RGB, you can imagine the green, the brown, you know, like
Gray.
the gray. Yeah. You have those color tones. And so there's just so much more variation probably in the DINO
Yeah.
V3
Yeah.
pre-training data set.
I think it's a really interesting thing. I think should we fast forward to how we kept going? So we had
Yeah.
the expert embeddings, you know, the ImageNet.
Yep.
I think, you know, we tried you tried a bunch of experiments. We tried some other ImageNet-esque, you know, same bucket of type of model of, you know, like tap into this net pre-trained model, grab the
SimCLR,
vector. Yeah, SimCLR. And I feel like that stuff all kind of worked. And then I think we tried to combine what expert embeddings were good at with what these
Yes.
spatial embeddings were good at, right? So we like tried to, like, again, the dumbest possible thing ever, smash these vectors together, concatenate them.
Yep.
We did some fun change detection stuff. So imagine you have like an embedding over 2020 and an embedding over 2021. You concatenate those 2 years into a change vector, basically, right? It's like the before vector and the after vector as a single embedding.
Yep.
And that was super, super interesting. And we spent a lot of time exploring that, right? Because it was like, because there's just so much more signal, because like changes
Specificity.
so much more specificity. It's almost like, I think at the time I was thinking how it was almost the opposite of like the problem of where you can't just take the difference of Landcover maps, because
Right.
what you're doing is propagating the error from one year to the other. But this was kind of the opposite, right? Because it was like you keyed in on a specific year at a specific place. You keyed in on the exact transition that happened, and that particular style of transition is so much more unique than like vegetation to built area, right? And so it ended up working super, super well.
Yep. Yeah, the change search stuff was really, really cool.
Yeah.
But you know, I think having had some time to think about all of these things, when I thought about all the different things we had solved using embeddings, I just always could find a way to do it without the embeddings, if
Of
that
course.
makes sense.
Of
right?
course.
And then it always made it hard to justify, like, is this tool that we're using actually useful? Or is it sort of pulling the wool over our eyes in some ways? Like, yes, it's making some part of the job easier, but if we would just sit down and think deeply about every single problem we're trying to solve, we could probably find a way to do this without embeddings.
I think what we were trying to figure out is something that gets you 80% in all these classes of problems pretty quickly valuable.
Yep.
And does it provide enough value such that you don't have to think as deeply about each specific problem, but get it to 95%?
Yep.
Or, you know, like, I think that's like the value proposition we were trying to explore is like, is this a tool that will be useful in the world? I'm not sure. I still know what the answer is to that, to be honest.
Yep. Yeah. I thought yes, and I've used it since to solve, you know, problems for customers or whatever. But again, I solved the problems and then I went back and thought about it and I thought, well, could I have just done this without embeddings? And I think the answer is yes, or yes to some degree, right? I think this also makes me think about something I've been thinking about, which is what properties do we want embeddings to have in the context of search, right? Like if you click on a thing and you're able to interact with the results and say more of these kind, fewer of these kind, you know, and sort of iteratively search, then what base properties do you want your embeddings to have? And I think it's sort of like you want them to have, and I hope I get this right, high recall across a lot of things you might be interested in at the expense of precision. So I think what you want is you want a lot of results, and you don't want
You want
to
a lot of
leave-
false positives.
Yeah, because you can filter through those easily.
Yeah.
Right. Like once you have a human in the loop, the human's job is actually to filter
Yeah.
through the false positives.
You
Like,
don't want to
they're the-
miss anything, though.
Exactly, because if you miss something, you're never going to find it, right? And
I think that's basically where every embedding struggles.
yep. And this was my criticism of the Google embeddings that had been, in my opinion, really sort of constrained to specific geographic areas. I think that's like basically like an opinionated design of the embeddings, right? Like, oh, you guys definitely want this, but what if I don't want that and I want something else? You know, what if I want to detect a more broad class of vegetation than what you're confining me to because this is an ecoregion in Alabama, right? And now I can't go and get those other potentially similar samples because you just somehow constrained me in this way. And so it kind of resolves to like a Landcover plus problem.
I think that's exactly right. It's like Landcover plus. Yeah.
Yes, that's what you want, right? Like you want things to be semantically meaningful, which Landcover kind of is, but you want a bit more semantic meaning than just built area versus bare ground. You want like building shaped this way, or field that behaves in this way, or something like that.
And if you're working in the Earth Engine ecosystem, which I almost always am, and you're using Dynamic World for, let's say you're doing like year over year urban change, and you're using Dynamic World for that, right? And you're taking like a year of Dynamic World, you grab the mode, you filter to the built area class, and you go look at that on the map, it's super blobby.
Yep.
So like the built areas that it's capturing are, you know, they're just really, really bubbly.
Yep.
I don't know how else to describe it. They're just,
Yeah,
they're like
blobby.
fat detections. Yeah. It's like,
round.
It's not just capturing the impervious surface. And, you know, to be fair, maybe that's how they're actually defining built areas. I'm not here to like argue that that's right or wrong, but like, I think one of the, you know, the way I feel like I could use embedding fields on top of that is to basically like make it less blobby, or to like basically start with that and boom, do a few labels of a particular type of impervious surface that I'm interested in, and it's off to the races, right? Like that's an easy problem for embedding fields.
Yep, absolutely. And I think if you think about it, if you think about embeddings as sort of Landcover plus you know, solutions, then actually the way to solve a lot of problems reveals itself. Like one of the examples of embedding fields was do similarity search to find grain silos or something like that. And it was I can't remember where it was, maybe Iowa, somewhere where there was a lot of grain. You know what I mean?
Yeah.
Like, and not that much built area.
Yeah.
And I bet if you took their target area and you just looked at the built area pixels,
right.
a lot of them would already show you the grain silos, and then you could just sort of, I would say, fairly easily manually filter out the non-grain silo pixels, right? And so, yes, this was a cool demo. You know, like, oh, we're doing similarity searching, we're finding grain silos, look. But again, if you just take the lens of Landcover Plus, you see another way to solve this exact problem, right? It just takes a bit of creativity, I guess, or just going to look at the data.
But maybe there's, you know, maybe there's value in the fact that you can just not think as deeply about what you need to solve and basically kind of solve it with one tool. You applied the same way.
Do you feel that way about like AI coding?
I don't.
Yeah, that's what I mean, right? And I think it's the same. I think it's analogous. It's like you don't want to offload your thinking, right?
Yeah, right.
And I think I think you just learn more by trying to solve a problem yourself or code up a problem yourself. And I definitely do use AI coding tools, but
Yeah, every day.
but I think it's like knowing when to say, okay, like how am I going to solve this problem in a way that, for me, learning about the problem is very important. Like I kind of don't want something to just one shot something for me.
Right.
Probably because that means that I'm about to get automated away anyway, and also just because I don't feel like I'm learning anything about the problem.
I think the other thing this exposes is something I guess I've been thinking a lot about, which is like, how much you have on the line when you produce something, or
Right.
like how high consequence is it when you make a map or you say that these things are here or not. And the amount you have on the line for a demo is 0 or negative. You could
Yeah.
care less whether there's false positives in there or it's kind of wrong. It's like, there was nothing on the line. This is a demo. This is cool. Just check this
Yeah.
out. And that's great. And then, but it's like, I think we've both worked in a number of places, and even in the like tech world, in this field, you're trying to find product market fit. You're building all kinds of models to make all kinds of maps, and or you're claiming
Yeah.
accuracy for these maps. You're trying to sell them to customers, and it's like, in a lot of those situations, there's kind of not a lot on the line either, right? Because
No.
you're like trying to get some business from a customer, so you're like showing what's possible and how validated is that, and you cherry pick your results. And I am extremely guilty of this, so I'm not like placing judgment on anybody who has had to do this. I mean, I've had to do this a lot, and now I'm in a position where in some ways the work I'm doing is the simplest, but the consequence of the things that I make is the highest in the validation sense, or in the this can't be wrong sense. And
Yeah.
when you are in that world, tools that make things easier for you or offload some of the thinking that you have to do or some of the data exploration you have to do is even harder to trust than it would be originally, because now you really don't know whether it's right or not. Some stuff's easy to validate, right?
Yep.
But
Yep.
visually, but some stuff's not. And
Yep.
and that makes a lot of this stuff pretty problematic.
Yep. Yeah. Absolutely. I think, again, definitely good for demos. And I do see a world where, accelerating highly imperfect, low consequence mapping is valuable, right? Like, I just feel like maps compound upon one another, right? Like, often when I'm trying to solve a problem, I'll pull in. The first thing I do is check if someone's already tried to solve it, or if they've
Yeah.
solved it for a different year or in a different place.
Right.
And I'll pull that map in, I'll intersect it with something else, I'll pull another data set in. And I think, embeddings can help you make those kinds of starting point maps when you don't know where anything is. Like, where is the aquaculture? Like, where's most of it? Where's some of it? I think the problem is when you're making a map and you're saying, here is all of it, or here is, and it's important to have all of it.
Right,
Or it's important,
right.
you're trying to measure something. So I think, yeah, that's definitely like maybe there is, if we had a tool that everyone could use and just create maps, like upload GeoParquet files or GeoJSONs of things they searched for and found, or something like that. Maybe
A
there would be
marketplace.
value in it. A marketplace. A marketplace. Some sort of open data service. Yeah. Yeah. I think, maybe there's something there. What I don't think is what I'm not too bullish on is sort of like, we are going to build the business of embeddings and it's worth this much. And everyone is going to use embeddings because it's just the easier way to do things. I don't really buy that. Yeah.
The other like super jaded view I have of this is that the reason this is such a big deal now is because like basically we've run out of new problems to solve with Earth observation data. And so
that is very jaded, Krishna.
like basically we've run out of new problems, and so we instead envision new approaches and tools to solve the same problems we've already solved.
Yep. Yep. I think
I don't fully believe that, but there's a part of me that thinks about that sometimes.
There are a lot of people try to justify their existence via embeddings for sure. Right? Like I think where, we could be spending money on actually solving the problems they claim to be able to accelerate. I think for sure there's a sense of like, how do we make the next exciting thing of freely available Earth observation?
Right.
I would love to just see some like harmonic regression coefficients over Sentinel-2 by year. I mean, arguably that's what these embedding fields are to some degree. I would love to see.
I think they're more than that, just from the amount of data that's going into each pixel, right? I mean, it's a ton of data sets.
They're trained. I would not be surprised if a lot of the variance they'd learn was explained by harmonic regression,
sure,
and a trend line or something like that,
But why do you want a database like that? You can do that on the fly in Earth Engine, right?
That's true. Yeah,
I mean, I guess I don't know why you would make that.
I gotta wait for my tasks to run. I mean, I do. Simon, if you're listening to this, please give me a task uplift in Earth Engine. No, I think it's true. I could just run that. I do think there is value in having something just there.
Yeah, of course. Like computed already. Yeah,
pre-computed. I mean, honestly, I would love annual composites masked by Cloud Score Plus. And I know it's not a big deal to get them or generate them, but like that's got to be high leverage, right? Like how many people are running it with the default Cloud Score Plus parameters every day?
I mean, I am like every day. I don't advocate for that. I feel like we can just run that on the fly as we need to.
Yeah, but what if you want the pixel? Now you got to wait.
Yeah, I'll wait a little. I mean, I think also, so everybody's opinions on all of these things are colored by the things they work on, and
yes,
I'm rarely working on global scale stuff these days. It's all regional, and so again, that's why Earth Engine is this amazing tool for me, because I actually can just compute everything on the fly, and I'm exporting stuff all the time. I'm creating assets of stuff that I'm going to use over and over again all the time, but I can always I can start from zero and just build the thing that I need over the place, and it's just all from the raw data, and it's truly beautiful to be able to do that.
Yeah. But say you want to create embeddings, which
the thing is, it's like if you're doing global composites, for example, it's like you've then created yourself a really hard problem, because your cloud parameters shouldn't be the same everywhere in the world. So how do you do the parameterization? So then that's a science project, and then it's you start unraveling the onion of what it takes to do this well, and then you find all the places in which your composite sucks, and then you say, well, this was a failure, but but the approach is great, right? It's just hard to generalize across the world.
Yep. No, I think you're right. It's true that only one of us has run a global model on Sentinel-2 data and picked at those problems. Yeah.
And looked at it and realized it kind of sucks everywhere.
Yep. Yeah. Global. We got to go global.
Global.
Yeah.
Oh man.
Well, how long have we been yapping for?
We've been talking for a while.
59 minutes.
I think we have done our first episode justice.
Yes, I think we have two. Cool.
Thanks everybody for listening. Thanks all 4 listeners.
Yes. I know. Oh wait, hold on. Thanks Zoe, who I know is definitely going to listen.
Zoe.
To this. I thought it's an hour. I don't know if Zoe's going to listen to an hour. But
we'll tell Zoe to skip to the end to hear this part, and then
skip
be like,
to the end, Zoe.
Yeah.
Yeah. All right. Cool.
Cool, man.
Thank you all. All right.
Talk to you
Bye.
later.